Hey guys, in this video I'm going to teach you the alternate definition of the derivative. I'm going to show you why it makes sense, what to do if you forget it, and I'll also show you a ton of examples so you understand it completely and can ace your next exam. So let's start with what it actually is and how you can get the formula if you ever forget it. If you just want to see the examples, please look for the timestamp in the comments or description down below. So the formula for it is just f prime of c, the derivative at point c, is equal to the limit as x approaches c of f of x minus f of c all over x minus c. So what does this formula actually mean though? Well, to understand it, let's draw a graph and then a function. And let's label a point, which we'll just call it C. And let's label another point, which we can just call, let's call it X. Okay, so how do we get the Y value at point C? Well, the graph we drew is a function since it passes the vertical line test. So if you have a point and input that point into a function, the output is just the Y value. So the Y value is just going to be f of c for the point C. And the same logic applies to the point X. So the Y value is just going to be f of x. So let's write out the coordinate pairs for each of these points. So instead of x comma y, it's going to be c comma f of c. And for x, it's going to be x comma f of x. Okay, so now let's draw a secant line between these 2 points. And a secant line is just a line that intersects a curve in at least 2 points. And since we have 2 points of intersection in this case, it's a secant line. So since we have the coordinates x comma y for these 2 points, we can find the average slope between the 2 points, or the slope of the secant line. So we can write m secant, which stands for slope of the secant line, is equal to y2 minus y1 over x2 minus x1. And now we can just plug in f of x for y2 because that's our y2 value. So we're just going to have f of x, and then y1 is just f of c. So f of x minus f of c all over, and then our x2 is just going to be x, so all over x. Then x1 is just going to be c, so all over x minus c. So now we're really close to being done. We almost have the formula for it. So we just need the slope of the tangent line at c now. And if we get that, we'll have the derivative at the point C. Just like, tangent line look like that. We want the slope of that line, and that'll give us the derivative. So to do this, all we have to do is take the limit as x approaches c. And this makes sense because if x approaches c and gets infinitely close to it, the gap between them will become infinitely small. So the key here is to realize that when you take the average slope of points that get closer and closer together, it becomes a better approximation of the slope of the tangent line at the point we're interested in. So taking the limit as x approaches c means they are infinitely close, so we get an infinitely good approximation, which means we're getting the slope of the tangent line at point C. So we can just plop in this formula to the limit, and we're going to have the limit as x approaches c of f of x minus f of c all over x minus c. And as we can see, this matches our original definition I gave you earlier. So that's how you can get the formula if you ever forget it. So our first function is going to be f of x equals x squared minus 5, and we want to find the derivative at the point c equals 3. So plugging in c equals 3 to the formula above, we're going to have the limit as x approaches c of f of x minus f of 3 all over x minus 3. Now because we know what f of x is equal to, we can just plug that in to the f of x in the limit. So we're going to have the limit as x approaches 3 of x squared minus 5. And then f of 3, if we just plug in 3 to f of x, we're going to have 3 squared, which is 9, minus 5 is 4. So it's going to be minus 4. So negative 5 minus 4 is just negative 9. So it's going to be x squared minus 9 all over x minus 3. So now we can just use the limit techniques that we know to solve this limit. So first, let's try direct substitution. So it looks like if we plug in 3, we're going to get the indeterminate form 0 over 0. So we can't just directly substitute it in. But it looks like if we factor the top, something might cancel, so let's try doing that. So x squared minus 9 is just x plus 3, x minus 3 if you factor it, over x minus 3. And then we can just cancel the x minus 3's. So we're going to have the limit as x approaches 3 of x plus 3. Now we can just directly substitute it in, and we're going to get it's equal to 6, which is equal to f prime of 3. That's the derivative at that point. Let's move on to the next example. So let's do f of x is 3 over x, and we want to find the derivative at c equals 4. So let's just plug this into our formula. So it's the limit as x approaches 4 of f of x minus f of 4, because 4 is the c value, all over x minus 4. Now we can just plug in 3 over x for f of x. So we're going to have the limit as x approaches 4 of 3 over x minus 3 over 4, because f of 4 is just 3 over 4. And then it's over x minus 4. Now we can try direct substitution again, but we're going to get the indeterminate form 0 over 0. So we're going to have to simplify this limit a bit more. I think we should get common denominators in the top to simplify it more, because I don't like how there are two separate fractions in the numerator. So let's try that first. So getting common denominators, we're going to have multiplying 3 over x by 4 over 4, we're going to have 12 over 4x, which is equivalent to 3 over x. And then we can multiply 3 over 4 by x over x. So we're going to have 3x over 4x, and you can cancel the x's and see it's equal to 3 over 4. And then it's over x minus 4. Now let's just simplify the numerator a bit. So it's the limit as x approaches 4. Always remember to write that, because we're taking the derivative, not the average slope, of 12 minus 3x over 4x over x minus 4. Now we don't like 3 fractions, so let's simplify that a bit more. So it's really over x minus 4 over 1, because x minus 4 over 1 is x minus 4. And then we can multiply by the reciprocal to cancel the denominator. So now we're going to have the limit as x approaches 4 of 12 minus 3x over 4x times x minus 4. Now let's look for something to cancel. Okay, so it looks like if we pulled out a negative 3 from the top, we would have x minus 4, because if you multiply negative 3 into x minus 4, you're going to have negative 3x plus 12, which is equal to 12 minus 3x, so they're equivalent. And now we can just cancel the x minus 4s, and we're going to have the limit as x approaches 4 of negative 3 over 4x. And then if we just plug in a 4, we're going to get negative 3 over 16, which is equal to f prime of 4. And that's our answer. Okay, let's move on to the final example. So our final function will be f of x equals the absolute value of x minus 6, and we want to find the derivative at c equals 6. Okay, so let's just write out the formula again. So it's the limit as x approaches c, but c equals 6, so the limit as x approaches 6 of f of x minus f of c, where c is 6, over x minus c, where c is 6 again. Okay, so now we can just plug in the absolute value of x minus 6 for f of x. So we're going to have that minus f of 6, but f of 6 is just 0, because 6 minus 6 is 0, and the absolute value of 0 is still 0. So it's minus 0, but that's redundant. We need to write that over x minus 6. So what we have to realize here is that this is an absolute value limit, and these limits often do not exist. So we have to remember that the limit from the left must equal the limit from the right for the limits to exist. So we can just test that for this. So we're going to have that equals limit from the right, and we just have to test to see if this is true. If it's not true, then the limit does not exist. So to test if it exists on each side, though, we have to split it into the piecewise function definition of absolute value. So if you remember, the absolute value of x is just negative x for x is less than 0. Less than. And it's just x for x is greater than or equal to 0. So this makes sense because if you plug in points to the piecewise function and into the absolute value of x, we realize they are equivalent. So to do the same thing for the absolute value of x minus 6, we just have to realize that, like the absolute value of x, one of them must be negative, so it's negative, parentheses x minus 6, and then x minus 6. So to determine the intervals, though, we just have to set the inside of the absolute value equal to 0. So it's just x minus 6 equals 0. So we just get x equals 6 there by adding 6 to both sides. So we know it's going to be like that. And then we just have to determine if it's greater than or less than for each of them. So to do that, we can just plug in points greater than or less than 6 into the absolute value of x and the piecewise function. So let's try a value less than 6, like 5. So if we plug 5 into absolute value of x minus 6, we're going to have 5 minus 6, which is -1. And then the absolute value of -1 is just 1. So let's see which of these in the piecewise function matches that if we plug in 5. So 5 minus 6 is just -1, and then the negative of a -1 is just +1. So that matches what the value is if we plug in 5 to the absolute value of x minus 6. So negative parentheses x minus 6 must be where x is less than 6. And this one must be where x is greater than or equal to 6. So now we can just use this for plugging it into the limits above here. So for the limit as x approaches 6 from the left, because it's from the left where x is less than 6, instead of writing the absolute value of x minus 6, we can just write negative parentheses x minus 6, and then this is over x minus 6. So these are just going to cancel, and then we find the limit is just equal to -1. And now let's do the same thing for the limit as x approaches 6 from the right. So it's going to be, because it's x is greater than 6 here, we can just use x minus 6 in place of the absolute value of x minus 6. And this is over x minus 6. So these cancel, and we're left with 1. So because -1 does not equal 1, the limits do not converge, so the limit does not exist. So that means we can say the derivative f prime of 6 does not exist. Does not exist. And that's our final answer. If you like this video, make sure to subscribe to my YouTube channel. Let me know in the comments down below if this video helped you or did not help you understand the alternate definition of the derivative. Thanks for watching.